and it's
Sorry,
on the transverse Ising model.
I just don't know how you do a presentation using PDF. Do you guys know?
Full screen, maybe?
Where's full screen? What's the key for full screen?
Like maybe view. Click on view. Try Control L. Oh no, this is.
Should I open it with Adobe? Do you know with Adobe?
Do you know this, David?
I apologize. Just 1 minute.
Yeah, Adobe would work. Now try view. One of them is full screen, somewhere, right?
All right. The things here.
Okay, so yes, unfortunately I'm neither Sergey Bravyi or Matt Hastings and was not involved at all in this work, but I'll do my best. So this is, what I'm going to present is based on these two papers, and the first one is joint work between those two guys, and the second one is a single author paper by Sergey. And this is about the quantum Ising model, which is also known as the transverse field Ising model, which is studied in physics as sort of a basic model of quantum phase transitions. But the motivation for this work was more from the computation side. So, well, there are two motivations listed here. One is quantum annealing. So D-Wave, as many people know, has built a device which, if you ignore noise, and that's a big if, but if you ignore noise, then it implements quantum annealing using the transverse Ising model. So it's interesting to ask the question, can we mathematically rigorously understand the performance of such an ideal quantum annealing device? The second motivation comes from the recent complexity classification result of Cubitt and Montanaro. So they studied local Hamiltonian problems where you restrict the terms in the Hamiltonian to a specific set of interaction terms S. And they classified the complexity of this problem as a function of that set S. And the transverse Ising model appears as one of four possible computational, well, we'll see. It appears as a central part of that complexity classification, and we'll see that some of the results presented here have some implications for that. Okay, so what is this transverse Ising model? So we have n spins or qubits, and they live at the vertices of a graph. We have a ZZ interaction between nearest neighbor spins with some coefficients that can depend on the edge. And we also have local magnetic fields along the Z and the X direction. So this, well, sorry. Okay, well, the X terms here are what makes this quantum. Otherwise, it would be the classical Ising model. So this is the plan for the talk. So the first part is going to be about using the transverse Ising model for quantum annealing. Thank you. The second part is going to be about the computational difficulty of estimating the ground energy of the transverse Ising model, and we'll talk more about the Cubitt-Montanaro result. And in the third part, we'll talk about restricting the transverse Ising model further to be ferromagnetic, and we'll see that there exist classical approximation algorithms which make this problem easy. Okay. So quantum annealing is going to be, for the purposes of this talk, defined in a slightly more narrow way than it's sometimes defined. So we're going to consider the problem of solving a classical optimization problem, which can be encoded as the ground state of a Hamiltonian which is diagonal on the Z basis. So here we have some Ising Hamiltonian, diagonal on the Z basis. And the strategy is going to be that we're going to start with a transverse field Hamiltonian, where the ground state is easy to prepare, and we're going to interpolate between these two Hamiltonians along some adiabatic path h of s, where s runs from 0 to 1. Now, in order to interpolate between these Hamiltonians, we're going to use a time-dependent Hamiltonian, which changes very slowly. And it's going to change over some total evolution time t, and t is chosen so that the Schrodinger time evolution is essentially adiabatic, so you remain close to the ground state, the instantaneous ground state. And so under that condition, at the end, we will have prepared the ground state of this classical Hamiltonian, which was our goal. And how large does t need to be? Well, you can look to rigorous versions of the adiabatic theorem to find out, but the upshot is that you want the path to be relatively smooth because the time depends on the norm of the derivatives of the interpolating Hamiltonian. And you also want it to have a minimum spectral gap above the ground state, which is not too small. So as long as that minimum spectral gap decreases at worst inverse polynomially, then the algorithm will be efficient. And it's sort of with this definition of quantum annealing, it's still an open question to determine what problems can be efficiently solved. And that's not the question that is addressed in this work. Here we're going to consider two quantum annealing machines, a simulator and a target. The simulator quantum annealing machine is going to be restricted to transverse Ising model Hamiltonians. So this is the sort of thing that we imagine that one could, in principle, build in the lab. The target quantum annealing machine, well, that only exists in some theorist's mind, and that's going to be also restricted to some class of Hamiltonians, but maybe it's a slightly bigger class. So, for example, you could consider the class of all two local Hamiltonians, and we'll go back to that example in a moment. And the question is, can the simulator efficiently simulate the target? And so, before talking more about that, maybe we should say what we mean by efficient simulation. So here is the definition of efficient simulation, which is going to be used in this talk, but it's not so important that you look at all these things. The main thing is that the simulator's spectral gap is at least that of the target. The number of qubits in the simulator is polynomially bounded as a function of that of the target. And if you look at the ground state at s equals 1, which is supposed to encode the solution, here we have psi in the target Hamiltonian, and in the simulator Hamiltonian we should have some encoding of psi, which you can, which is sufficiently simple that you could still get the solution from this state. So under these conditions, the adiabatic theorem will guarantee that the time required for the quantum annealing algorithm using the simulator is a polynomial function of the time required for the quantum annealing using the target. Okay, so let's go back to this example that I mentioned, and we'll see that, well, efficient simulation of the class of all two local Hamiltonians is unlikely if you're using a simulator quantum annealing machine which is only capable of implementing transverse Ising model Hamiltonians. So this is not quite correct. So here it's known that quantum adiabatic algorithms using two local Hamiltonians can perform universal quantum computation. Here we're talking about quantum annealing, where the interpolating Hamiltonian is two local, but the final Hamiltonian is restricted to be classical. So this result doesn't, strictly speaking, apply, but maybe we can still take it as evidence. On the other hand, transverse Ising models, if you consider quantum annealing with these models, then the most you can do is BQP intersect post-BQP. And post-BQP is contained in the polynomial hierarchy, but BQP is not thought to be contained in the polynomial hierarchy. So it's unlikely that that transverse Ising model Hamiltonians can simulate all two local Hamiltonians in this quantum annealing sense. So that means that we have to restrict the class of Hamiltonians that we want to simulate. That is to say that our target machine can implement to some smaller class. And the class that we're going to consider is the class of stochastic Hamiltonians. So this is a definition of stochastic Hamiltonians. We have a local Hamiltonian, and each matrix element of the Hamiltonian is real, and the off-diagonal matrix elements are non-positive. So in the condensed matter lingo, this would be said to be sign problem free. Many interesting Hamiltonians have this property. So for example, the transverse Ising model has this property. The Heisenberg model on a lattice has this property. The toric code has this property, and lots of other examples. And for two local stochastic Hamiltonians, we can be just a little bit more explicit. Any two local stochastic Hamiltonian can be written as a sum of these terms with positive coefficients. So the first result in this talk is that transverse Ising model quantum annealing can simulate arbitrary quantum annealing with stochastic two local Hamiltonians. And furthermore, even if we add to our stochastic two local Hamiltonian a k-local diagonal term, the simulation is still possible and is efficient. And this is kind of interesting to add k-local diagonal terms because, for example, quantum adiabatic algorithms for exact cover and k-satisfiability are in this class. And furthermore, you can even restrict the quantum annealing machine to transverse Ising models on degree 3 graphs. Okay, So that now we're going to switch gears and talk about estimating the ground energy of these models. So we're going to be working in the framework of local Hamiltonian problems, which was introduced by Kitaev. So in this type of problem, you're given a Hamiltonian and two thresholds. And if it's a yes instance, then the ground energy of the Hamiltonian is less than or equal to the lower threshold. But if it's a no instance, it's greater than or equal to the upper threshold. And you're promised that one is the case, and you have to decide which. And to understand the complexity of these problems, let's just review some complexity classes. So in the setting of Merlin-Arthur games, we have Merlin, who's has unlimited computational power, and Arthur, who has, well, he's polynomially bounded. And they're both given an instance of a yes or no problem. And Merlin's goal, no matter what the instance is, he's going to try to convince Arthur that the answer is yes. So he sends a proof to Arthur, which could be, for example, a bit string. And Arthur's going to run it through some kind of verification procedure and decide to accept or reject. And so, you know, NP is the class of problems which have such reliable verification procedures with zero error. And we also know that QMA is the class of problems where you have a verification procedure of this form, but where the proof and Arthur's computation to verify can both be quantum. So now the proof can be a quantum state, and Arthur runs it through a quantum computer to do verification. It's also, whereas NP is deterministic, QMA is probabilistic. So the verification procedure only succeeds with some probability. And now here's a funny class that probably, well, only some of you have seen, which is called, actually I'm not sure how to pronounce it, but let's go with stock MA. So this is similar to QMA, and it has a really kind of strange looking definition, but well, I think the results that are being presented here show that it's kind of natural. But it's the same as QMA, but Arthur's verification circuit can only use reversible classical gates, and the measurement at the end is of a single qubit in the X basis. And then Arthur accepts if and only if the measurement outcome is plus. So this was introduced in this paper by Bravyi, Besson, and Turhal. Okay, so now here is the relationship between stock MA and other complexity classes, including many that I have not defined. The most important thing is that stock MA contains MA, which is the probabilistic version of NP. It's also contained in QMA, and it's also contained in AM, which is like MA, but where Arthur and Merlin share a random bit string beforehand. Okay, so now let's talk about the complexity of local Hamiltonian type problems. So in the classical case, a sort of seminal result was proven by Barahona, who showed that computing the minimum energy of the Ising model in the classical case is NP complete, and even in a 2D geometry. And then in the quantum case, well, the study of this was initiated by Kitaev, and then a sequence of works improved the results, and now we know that computing the ground energy of a k local Hamiltonian is QMA complete whenever k is greater than or equal to 2, and even in a 2D geometry. And so here's where stock MA comes in. So it was shown that the local Hamiltonian problem for these k local stochastic Hamiltonians is stock MA complete for k greater than or equal to 2. And so now, having set the stage, I'll state the second result of this talk, which is that the local Hamiltonian problem for the transverse Ising model on degree 3 graphs is also stock MA complete. So this, I think, is very surprising, because you might have thought that the transverse Ising model has some extra structure which makes it easier to solve the ground energy problem, I mean, by exploiting that structure. But what this says is that it's not, actually. It's just as hard as the general problem for stochastic local Hamiltonians. And this result, as I mentioned at the beginning of the talk, also has implications for this complexity classification by Cuban and Montanaro. So let me just review precisely, or slightly more precisely, what it is that their result says. So they consider a problem that they called S local Hamiltonian problem. And S here is a set of interaction terms. And so given a set of interaction terms, you consider the class of Hamiltonians where those terms can appear with arbitrary real coefficients. So for example, this set S would correspond to the transverse Ising model local Hamiltonian problem. So it's just a local Hamiltonian problem with a restricted set of interaction terms, but we want to consider it as a function of this set S. For every set S, there's a different problem. And what they proved is that there's only 4 possibilities. Depending on the set S, the problem could be contained in P, NP complete, QMA complete, or polynomial time reducible to the transverse Ising model local Hamiltonian problem. Now, what this result, which I presented on the previous slide, says is that the transverse Ising model local Hamiltonian problem is just as hard as the local Hamiltonian problem for general stochastic Hamiltonians. So the improved classification is, in this 4th case, the problem is stoch MA complete. Okay. So that brings me to now part 3 of the talk, which is about the ferromagnetic transverse Ising model. So in this part of the talk, what does ferromagnetic mean? It just means that all of these coefficients have to be greater than or equal to 0. So this interaction term makes the spins all want to line up in the same direction. We're also going to restrict to the case of a uniform Z field. So notice that G doesn't depend on U anymore on the spin. The transverse field can still depend on the spin. Okay. And if I remove this transverse field, then I get the classical ferromagnetic Ising model. And so I'm going to spend a slide just talking about what's known about that model. So first of all, if you think about the classical Ising model, if you have a uniform Z field, then it's fairly easy to see that the ground state is always either all spins up or all spins down. So it's completely trivial to compute the minimum energy. And if you have, if you generalize this to arbitrary Z field, so a Z field that can depend on the spin, then, well, it's still classically efficiently solvable, but not quite as trivial. And then there's sort of these interesting results about approximating the partition function. So it's known that approximating the partition function of the classical Ising model in the ferromagnetic case is sharp P hard. But if you ask for a multiplicative error, or an approximation algorithm that achieves a multiplicative error delta, then there is a polynomial time algorithm which has this running time, which is kind of crazy. It's not a practical algorithm. This is in the case of a uniform Z field. But interestingly, there's also a hardness, or a sort of a result which suggests hardness of approximation in the case where you generalize to arbitrary Z fields. Okay, so the third result in this talk is a polynomial time approximation algorithm for the partition function of the ferromagnetic transverse Ising model. So this generalizes the Jerman-Sinclair result to the quantum case. And so just to be clear about what this algorithm does, it takes as input the parameters of the model, which are these edge weights that are all positive, the uniform Z field, the transverse field, as well as a parameter that controls the approximation. And it has this running time, and it achieves with high probability an approximation to the partition function with that multiplicative error. And if you now take a log, then you get the free energy, and that converts the multiplicative error into an additive error. And so you one of the implications of this result is an algorithm which estimates the free energy with additive error delta in time polynomial as a function of these parameters. And if you take the temperature to be low, then you can approximate the ground energy in this way. Okay, so now I'm going to sketch the proofs, and we're going to go in reverse order. So first I want to tell you about the algorithm for approximating the partition function of the ferromagnetic transverse Ising model. So we're going to just write the Hamiltonian this way. Here A is the classical piece, and B just contains the X terms, the transverse fields. And this algorithm just puts together sort of 3 known facts in a sort of intuitive way. So I think I can explain it on this one slide. The first step is that you take this operator e to the a plus b, and you use a sort of Trotter-Suzuki approximation with some number of slices r. Now if r is infinite, then we know that this operator is equal to e to the a plus b. But when when R is finite, then you just get some approximation to the partition function, and you can ask, how big does R need to be to get some multiplicative error delta? And so, this fact is proven in Sergey's paper that, as a function of these operator norms A and B and the error that you require, this is a sufficient bound on R. The second fact is what's called the quantum to classical mapping. So this forms the basis actually for many quantum Monte Carlo algorithms and is sort of well known, which is that this operator, or sorry, this is just a number, it is actually equal to the partition function of a classical ferromagnetic Ising model with more spins than you started with. So the number of spins gets multiplied by R, and the way that this is usually derived is by inserting complete sets of states in between each of these R operators that we've put in here to get a sort of path integral. And then the third fact is just the fact we talked about earlier, which is that there exists already a classical approximation algorithm for the classical ferromagnetic Ising model. So putting those three facts together, well, that's how this algorithm goes. Okay. So now for parts 1 and 2, the idea of the proof in these parts has to do with the idea of perturbative reductions. So here we have a target Hamiltonian, or at each stage of the proof, we have a target Hamiltonian and a simulator Hamiltonian. And the goal is to somehow embed the target Hamiltonian in the low energy space of the simulator Hamiltonian. And the way this is done in practice is by using perturbation theory. So we have the simulator Hamiltonian has two terms. This is like a big term, and this is a small perturbation. And this term has some degenerate ground space. And you can think of the perturbation as like, exciting transitions to the higher excited states. And the condition under which this perturbation theory is going to work is where this energy gap is much bigger than the norm of V. And under that condition, you can expand, or you can compute an effective Hamiltonian as a perturbation series, and you can hope that that perturbation series emulates the target Hamiltonian that you wish to embed. So our goal is to have as our simulator Hamiltonian the transverse Ising model on degree 3 graphs, and as our target Hamiltonian a general stochastic 2 local Hamiltonian. But the way that the proof goes is to have a bunch of models in between and to have a sequence of these perturbative reductions, actually 6 of them. So, so these models, we don't need to go through all of them, but like here, this is the general transverse Ising model where we don't have the degree 3 restriction. This is a model of hardcore dimers, which actually we'll talk about in a couple of slides. Then we have hardcore bosons, which are like particles that don't want to come too close to one another. And here range 2 means they don't want to come within 2 vertices of one another, and range 1 means they don't want to come within 1 vertex. This hardcore bosons with controlled hopping is another model of hardcore bosons with some other restriction. And finally, there's the model that we want. Okay, so yeah, that's the way this proof goes. You just have a sequence of perturbative reductions, and it appears to be a lot of work. Well, so now, I wanted to present in the last part the idea behind one of those. Okay. So the hardcore dimers model. So first I have to define the models. The hardcore dimers model is a system of particles which live on a graph. But whenever you have a particle, it has a particle next to it. So these are dimers, okay? There's a range, which is like the minimum distance that separates 2 dimers, okay? So they don't want to be too close together. So here's an example of a valid dimer configuration with range 2 on a line. But of course, you could consider more general graphs. So the Hamiltonian has a bunch of terms, one of which allows the dimers to hop. and then some diagonal terms which depend only on which vertices are occupied. And the dimers can move locally. So for example, this configuration at the top could hop to the configuration on the bottom. There's a matrix element for that. But you couldn't have this transition because it breaks the dimer. So you move out of the dimer subspace. That's not allowed. And you also couldn't have this transition because then the dimers get too close together, and that's also not allowed because it's range 2 in this example. Okay, so I'm actually going to talk about these two reductions. So the transverse Ising model on degree 3 graphs to the general transverse Ising model, and then the second reduction from the general transverse Ising model to hardcore dimers was range 3. Okay, so the first reduction at a high level goes as follows. You want to emulate the transverse Ising model on a general graph using the transverse Ising model on degree 3 graphs. And the way this is done is to take each spin in the general graph and encode it using a one-dimensional chain of the transverse Ising model on a degree 3 graph. And that chain is designed so that it has 2 approximately degenerate states of low energy, which are going to encode the states of the qubit. And then by adding terms between these chains, you can emulate the ZZ and the X terms in the original transverse Ising model. So sort of you can see in this example that you go from arbitrary degree to degree 3. Okay. The second reduction, which I'll talk about, is to go from the general transverse Ising model to the model of hardcore dimers. And the way that this is done is you want to represent the states of the dimers using spins. So a spin being up represents a particle occupying the vertex, and a spin being down represents no particle occupying the vertex. And it is possible to write down an Ising Hamiltonian, which is just purely classical, and whose ground states are this dimer subspace. Okay, so that's the first step. But then once you've got the dimer subspace enforced, you need to add the terms which appear in the Hamiltonian, so the hopping term and the diagonal terms. And the way this is done is by, so you can emulate the hopping term using the transverse field. And there's sort of a way of understanding that using second order perturbation theory. But maybe I won't get into that. Okay. So I'll just conclude with some open problems. Right, so this first one, the result which was shown is that transverse Ising model can simulate quantum annealing with 2 local stochastic Hamiltonians as well as k-local diagonal terms. But we don't know if it can simulate quantum annealing with general k-local stochastic Hamiltonians. So that's one open question. Another question which I personally really like is the second one. So if you consider quantum annealing with stochastic Hamiltonians, what is the power of that? I mean, is there some subclass of BQP that tells you what that is capable of? Yeah, so more efficient algorithms for the ferromagnetic transverse Ising model. We saw that the scaling was not practical. And the second one is that this class stock MA does not have amplification for completeness and soundness, so it would be nice to see if that's possible. Okay, thank you.
So we're actually not going to take questions because David isn't a co-author on this work. Instead, we have a coffee break, which it ends in 20 minutes, so enjoy it. See you back here soon.